In this video, I want to start talking about probability for discrete random variables. But in order to do that, we have to define what a discrete random variable actually is. And the best way to do that is by contrasting it with a continuous random variable. So think about a discrete random variable as a variable that can take on a discrete set of values or a discrete value set. We usually use a capital X to denote a discrete random variable. So let's say that we want our discrete random variable capital X to model the number of heads we get when we flip a coin 2 times. Well, when we flip a coin twice, we only have 4 possible outcomes. We have heads, 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 tails, tails, heads, or tails, tails. These are the only things that can happen. So X models the number of heads that we get when we flip a coin twice. Well, we can see here that if we get this first outcome, then we get 2 heads. If we get this second outcome, we get 1 heads. If we get the third outcome, we get 1 heads. And if we get this fourth outcome, we get 0 heads. So if X is a discrete random variable that models the number of heads we get when we flip a coin 2 times, then X can only take on the discrete set of values 0, 1, and 2. There are no other values that X can have. X can't be 1.5, it can't be 7, it can't be 0.5, it can't be any values other than 0 or 1 or 2. So we would call X a discrete random variable because it can only take on these discrete values or these particular points. We would contrast that with a continuous random variable that can take on all values along a continuum. An example might be if I want to model the heights of all of the people in the world. So let's say I'm doing this in inches. Someone that's 5 feet tall is going to be 60 inches tall. So they're going to be 60 inches tall. There's going to be a lot of people who are 61 inches tall, some people who are 62 inches tall. There's going to be some people who are 59 inches tall. But there are also going to be people who are 59.5 inches tall. There's going to be people who are 60.5 inches tall. And there's going to be people who are 61.5 inches tall. Furthermore, there are going to be people who are 60.25 inches tall. And if I start measuring even more finely, I could say people who are 60.2 inches tall, or I could say people who are 60.3 inches tall. And I could get more particular and say that there are people who are 60.255 inches tall. Now, at a certain point, our ability to measure the difference between the height of 2 different people is just going to reach its limit. We may only be able to calculate someone's height to a certain number of decimal places, and we can't keep getting more and more and more precise. So you might be tempted to think that this is also a discrete random variable, because maybe we can only measure someone's height precisely to 3 decimal points. And in that case, you could say that, oh, it's a discrete random variable where the heights can only be 60.255 and then 60.256 and then 60.257, and we can't have anything in between these. But barring our inability to measure smaller and smaller differences, that's not really the point we're trying to make. The point that we're trying to make is that people's heights generally fall along a continuum, and we have people that can take on all of these values for their height. It's not like we're limited to people are exactly 59 inches tall, or exactly 60 inches tall, or exactly 61 inches tall, with no possible way to take on values in between. Everybody's height is going to be slightly different, and so we would think about something like this as a continuous random variable versus something like this, which is very clearly a discrete random variable because the value can only possibly take on exactly 0, exactly 1, and exactly 2, nothing else. Now, if I want to create a probability distribution for a discrete random variable, all I need to do is identify the values that the discrete random variable can take on. So like in this case, it can take on 0, 1, and 2. And then I need to find the probability that it will actually take on each of those values. So what is the probability that the value of the discrete random variable x is 0? What's the probability that it's 1? What's the probability that it's 2? Well, in this distribution here, the probability that x is 0 is the probability of getting 2 tails when we flip a coin twice. Well, we know that there are 4 possible outcomes, and one of them is an outcome where we get 0 heads. So 1 out of the 4 outcomes gives us a value of 0 heads, which means that the probability of getting 0 heads is 0.25 or 25%. If I do that same calculation for 1 and 2, I get this probability distribution table for the discrete random variable x. You'll see the capital X here. I can see the values that it takes on, 0, 1, and 2, and then the probability of getting each value. This tells me that there's a 25% chance of getting 0 heads, that there's a 50% chance of getting 1 head, and that there's a 25% chance of getting 2 heads. Keep in mind also that since all probability distributions sum to 1 or 100%, if we know the probability that x takes on one of these values for every value but 1, so let's say we know that this first value is 0.25, that the second value is 0.5, but then let's say that we don't know this value at all. We don't know what this value is. Well, in order to calculate it, so we say 1.00 minus 0.25 minus 0.50, and we get 1 minus 0.25 is 0.75, minus 0.5 is 0.25. So this is equal to 0.25, and then we could go ahead and put in here 0.25. We can also show the data from this table for the discrete random variable in a probability distribution. And that would look something like this. So across the bottom, we can see the values that x can take on. We know x can either be 0 or 1 or 2, so we have 0, 1, and 2 across the bottom. And then we just plot up the vertical axis the percentage chance that each of these occur, or the probability that each of these occur. So we have a 25% chance that x will take on the value of 0, so we graph this 0 bar here up to 0.25. There's a 50% chance that x takes on the value of 1, so for 1 here, we plot this all the way up to 50% or 0.5, and there's a 25% chance that the discrete random variable x takes on a value of 2, meaning that we get 2 heads when we flip a coin 2 times. There's a 25% chance of that, so we graph this bar up to 25% or 0.25. And no matter how many values our variable can take on, we can still just line those up side by side in our probability distribution and graph the probability for each one. Now, the last thing I want to talk about is mean, variance, and standard deviation for a discrete random variable. For the mean, which we also call the expected value, since the function is not continuous, what we have to do is we have to weight each of our probabilities by the value that the variable takes on. So in other words, we say mu sub capital X is the discrete random variable. We could also express that as E of capital X, or the expected value, is going to be equal to, and all we do here is we multiply these two values together. So we say 0 times 0.25, we say 1 times 0.5, and we say 2 times 0.25. So the value that the variable can take on, 0, multiplied by the probability that that happens, so 0.25, plus the value that the variable can take on, 1, multiplied by the probability that that happens, 0.50, plus the value that the variable can take on, 2, multiplied by the probability that that happens, 0.25. And we could continue on even if we had more values, more possible values for x. In this case here, we just get 0 for the first term, we get 0.5 for the second term, and 2 times 0.25 is another 0.5. So the result then there is 1. What this tells us, since x models the number of heads we get when we flip a coin 2 times, is that we can expect to get 1 heads every time we flip a coin twice. So that's our expected value. We expect that most of the time we'll get 1 heads when we flip a coin 2 times. And then the variance, so the variance for a discrete random variable, again, we have to weight it just like we did for the mean or the expected value. So the formula we use, again, for variance, it's always sigma squared, but we put the capital X there to indicate the discrete random variable. And then we're just going to take the sum from I equals 1 to n, however many values we have, of x sub I minus the mean, mu sub x, and then we're going to square that, and then we're going to multiply by the probability of that particular value that x takes on. So here's what that looks like. All we do is we take the first value that x can take on, which is 0, and we subtract the mean. Well, we already found that the mean or the expected value was 1. So we get 0 minus 1 squared, and then the probability that x takes on the value of 0 is 0.25. So we multiply that by 0.25, and that's all that fancy formula means. We do that for every value that the variable can take on. So then we're going to add to that the next value. X can take on the value of 1. So we say 1 minus the mean. We square that. And then the probability that x will be 1 is 0.5. So we say 0.5. And then add to that the last value. X can take on the value of 2. So we say 2 minus the mean squared multiplied by the probability of 0.25. So 0.25. If we simplify that, we say 0 minus 1 is negative 1. Negative 1 squared is a positive 1. 1 times 0.25 is 0.25. 1 minus 1 is 0. 0 squared is 0. 0 times 0.5 is 0. So we get plus 0. And then 2 minus 1 is 1. 1 squared is 1. 1 times 0.25 is 0.25. So 0.25 plus 0.25 is equal to 0.5, and that is the variance of this discrete random variable x. And then the last thing is just standard deviation. And standard deviation is always the square root of the variance. So the standard deviation we denote with just sigma. We'll put the x there to indicate the discrete random variable. So sigma sub x is simply going to be equal to the square root of 0.5. And when we calculate that, it is approximately 0.71. So just remember that for a discrete random variable, when we find the mean and the variance, we have to do this weighted method where we multiply the value that the variable can take on by the probability that the variable takes on that value. And then in order to find standard deviation, like always, we just take the square root of the variance.